Oh, sorry about that. Actually, it got cut off because I forgot to plug in my machine. So this is just kind of the very end of lecture 3.1. So we stopped with this guy, right? We're looking at this matrix and we want to see what happens to it, the unit square rather. So we're looking at what happens to the unit square under the linear transformation t of x equals ax. And what we said was all you have to do is know what happens to t of 0, 1 and t of 1, 0 because of this property, right? These vectors span all of R2. And so we observed that t of 0, 1, this guy, goes to 0, negative 1, right? So it's now down here. And t of 1, 0 remains t of 1, it remains 1, 0, right? And so what you're getting this time around is a reflection of the square over the x-axis. Right, and again, you could notice that by just taking scalar multiples and showing that every time you're in here, you're getting smaller and smaller scalar multiples of those vectors. So in fact, this is not just true for these guys. You can take any scalar multiple you want, and that's in fact what you'll get down here. Just let R1 and R2 run between 0 and 1, and you'll show that this is the set that you get. And these two are a little bit more exotic. Let's compute here t of 0, 1 and t of 1, 0. Exotic in the sense there's more to do and in terms of multiplication and what the result will be. Right, so here, if I were to multiply this out, notice I get negative 1 over radical 2, and this time I get 1 over radical 2. Right, so in terms of the unit square, t of 0, 1 was here. Right now, it's going to be on the negative 45 degree line. So let me just draw this in. Right, so you're back here at negative 1 over root 2, 1 over root 2, right? So we're at this point. So it rolled. It was here, 0, 1, and it rolled that way, okay? And then same way here, t of 1, 0, if I look at it, take that matrix and multiply by 1, 0, what I get is 1 over root 2, and then, so I get 1 over root 2, and then 1 over root 2. So I get the corresponding point over here. Remember, this was here, now it rolled 45 degrees. So what seems to be happening is that I am rolling these guys 90 degrees, right? And so if I were to have taken this point, it would have rolled to 0, 1, right? And so what I get is this sort of rotation. Okay, so you get a rotation by 45 degrees. Okay, sorry, it should actually have the same length every time. So this should be it shouldn't have gotten any larger. It should just be this guy literally turned like that. It's still a rhombus, or it's still a square. In fact, it just out at a 45 degree turn. And this guy here, if I look at t of 0, 1 and t of 1, 0, here I get 2, 1. That's different. And this time I get 1, 0. Right? And so if I were to graph them, 0, 1 was here, right? Now 2, 1 is here. So I have that vector, and t of 1, 0 is 1, 0. So that hasn't changed. It's still this vector, right? And so this time you're getting kind of a stretched parallelogram, right? In comparison to what this unit square was. We call that a shear transformation. Just some examples, right? So if you're interested in the geometry or whatnot, you can tinker around with these. You get even more exotic ones as well, but this is kind of just an exposure, if you will. Okay, so very good. So give these problems a go, right? On linear transformations, it's all boiling down to just how you compute with functions and those two properties of matrices. Give them a go and see, let me know how it goes. All right, take it easy. Bye.